Very good evening to those who have joined, and I'm still waiting for others to join. Let's give 2, 3 more minutes for other people to join in. Then we'll start the week 3 tutorial class, and that will be on concept of water retention, soil water characteristic curves. So now I think it's time, and we can start today's session. And as we've already completed to week 5, but the week 3 and 4 are left, so we are just covering it back. And the week 3 is on concept of water retention and soil water characteristics. This course is on unsaturated soil mechanics, and it's instructed by Professor T.V. Bharat from IIT Guwahati, and I'm the PMRF TA, Mr. Satyam Tiwari from IIT Dhanbad. So, as we move on to week 3, we will first like to discuss the numerical we did in the last tutorial class, and we'll be solving it again in a greater depth. Okay. So, the first numerical, it says it's about direct shear test, and it says the shear box test results of the two samples of the same soil, but with different initial unit weights are shown in the table below. So, sample A did not show a peak value, but sample B did. Okay, so we need to determine the phi critical state, effective critical state friction angle, and the phi dash P at vertical forces of 200 Newton as well as 400 Newton for sample P. Okay, then we need to determine the dilation angle at vertical forces of 200 Newton and 400 Newton again for sample P. So as we can see, the results of two soil are given here. There are total 7 number of tests were there. So test 1, 2, 3 are performed on A, then 1, 2, 3, 4 for B. Okay. So if we simply plot this horizontal and vertical force on a graph so that to obtain the phi value from the test results, So how we can do that is we'll just draw a y-axis here and x-axis here. In the y-axis, we will plot the values of vertical force in Newton. Fine. In the x-axis, we will plot the second value, that is of. In the y-axis, we'll plot the horizontal force. Okay. So in the x-axis, we plotted vertical force. In the y-axis, we are plotting the horizontal force in Newton. So let's approximately fix the scale, and that's going to be, let's say here it's 200, 400, 600, 800, and maximum the value of the vertical forces are going up to 750. So 800 is fine. And in the horizontal, in the vertical direction, that is on the y-axis, we can plot 100, 200, 300, 400, and 500. Fine. So here, if you'll see, then if we plot the values of the test results from sample soil A, then we'll see the vertical force for the first one is 250, and corresponding to that, the horizontal force is 150. That's going to be here. So this one is the point. For the value of the second test, that's going to be 500. The vertical force. So somebody's trying to join. Okay, fine. So we were discussing this numerical of direct shear test, and we solved in the last class, but I'll be solving it again for more clarity. So we were plotting the values of test results of for soil A for the test 1, 2, and 3. So for the first one, the value is the vertical force is 250 and the horizontal force is 150. So we plotted 250 and 150 on our XY plot. Okay. And then for the second test, the value of the vertical force is 500. So that's going to be 500. And the value of the horizontal force is 269. So that's going to be somewhere here, right? And for the third one, that the value of the vertical force is 750 here. And the value of the horizontal force is 433. So that's going to be somewhere here, right? Or maybe a little lower. So if we plot these points in Excel, that will be the best practice. And now from this origin, if we best fit a line in these 3 points, then we'll obtain that as it has been shown that the sample aid is not so a peak value. Okay, and this is for soil A. Fine. So if we determine the slope of this best fit line, then we can determine the phi critical state value, right? So to determine the phi critical state, if you best fit the line in Excel, then it will be directly giving you the slope of the line. But here we can roughly do it like phi dash critical state, that will be equal to tan inverse. If I just take the value at 450 maybe, or maybe 500, the second one. So that will be tan inverse, the value of horizontal force, that's going to be 269, and the value of the vertical force, that's going to be 500. So what if we solve these values? That will give us tan inverse 269 divided 500. That's going to give you around 28.28 degrees. Fine. So now we can repeat the same practice for sample soil B. Okay, so for the soil B, the first test shows the vertical stress value of 100 and the horizontal stress 98. So that's going to be somewhere at this point, right? I'm denoting it with a cross, small cross. And for the test 2, it's going to be 200 by 175. So 200 by 175. Okay. And for test 3, it's 300 to 110. Okay, so 300 and corresponds to 210, a little about 200 here. And for the fourth one, it's going to be 400, corresponds to 248. So somewhere here, that's 269 and below that one. So if we plot the graph, a curve from these lines, that's going to be a curved line, right? A curve. So the same soil B, it shows a uh, it shows the behavior of dilute density. So that's why it's having a peak value. So we need to determine the value of phi dash peak, okay, the value of internal friction at 200 Newton as well as 400 Newton. So for 200 Newton, if you'll see, we can, let me change the color maybe. So for the 200 Newton, if we draw a line, that's going to be here. And for the 400, similar to the 400, if we draw a line, that's going to be here. So to determine the slope of these two lines, what we can do is that we can directly read the values from here, and there will be phi dash. So that's going to be phi dash peak at 200 Newton. That will be tan inverse. What is the value at 200 Newton? The horizontal force is 175 divided by 200 for soil B. And that's going to be tan inverse 175 by 200. And it will be around 41.19 degrees. Similarly, we can do it for phi dash at peak at 400 Newton. That will be tan inverse. The value at 400 is 248, the horizontal force. So 248 upon 400. Okay, so it will be tan inverse 248 upon 400. And it will give you a value of 31.79 degrees. All right. So these values are like mostly correct, but this one, if you'll like to obtain the exact value, then you have to plot the graph in Excel, then the best fit the line between these points. Okay. So now based on the values we have obtained, we can also calculate the dilation angle at vertical forces of 200 and 400 Newton for sample B. So phi dash critical is going to be the same. It is 28.28. So dilation angle at the vertical force of 200 Newton will be phi dash peak at 200 Newton minus phi dash critical state. So that's going to be at 200, it's 41.19 degrees minus phi dash critical is 28.28 degrees. So it's going to be 41.19 minus 28.28 degrees. And it will be around 12.91 degrees. Similarly, the dilation angle for 400 Newton we can obtain. It will be equal to 31.79 degrees minus phi dash critical is 28.28 degrees. So that will be 31.79 minus 28.28. It will be around 3.51 degrees. Fine. So we have obtained the critical state friction angle. We have obtained the peak friction angle at 200 and 400 Newton on vertical stresses, vertical forces, and the dilation angle for the same. Okay. So yes, these are the solutions which I have noted here from the book, but they are approximately the same, just that the value of phi dash critical state which they have calculated that's from the line, so it's going to be 30 degrees instead of 28.28 degrees. Okay, so fine. So in this problem, if you might be having any problem, then you can let me know. So with this, we move on to the next example, which says that at relative density of 50% and an air pressure of 100 kPa, which temperature leads to higher air density, either 0 degrees centigrade or 45 degrees centigrade. Okay, and the data which is given here is the molecular mass of dry air, WA, sometimes it's called WD, 28.966 kilogram per kilomole, and universal gas constant, molar mass of the vapor, that is WB. So these three things are given. So here the relative density is 50%. So if we see for if we want to determine the dry density of the air, then in that case we can use the formula UD WD upon RT. Okay, but if we determine the air density at some moisture content or the relative density that is given here, and in that case, we'll need to use this formula, that is rho A moist is equal to rho D, which we have calculated here, minus 0.611, and this term. Okay, this term includes the value of molecular weight of air, okay, or we can say dry air, and the molecular weight of mass of vapor, okay, water vapor, and the temperature in Kelvin. Apart from that, the gas constant, that's going to be relative humidity, that is going to be 50%, and the gas constant and the temperature, and the molecular weight of water vapor here also, right? So let's solve this problem. Okay. So to solve this problem, first we'll calculate the air density when it is dry. Okay. So in that case, we'll calculate the rho D. We'll calculate the rho D here. So the formula of rho D as written here is UD WD upon RT. Right. So we'll note down the values all in the same unit. Okay. The SI system, if we are following, then the value of UD as given here, that's going to be air pressure value is 100 kPa. So that's going to be 100. Okay, kPa is kilometer per meter cube. So we'll convert it to Newton. So 10 to the power 3. And the unit will be Newton per meter square. Then we'll multiply that value with the molecular weight of the molecular weight of dry air. That's going to be 28.966 kilogram per kilomole. So in the denominator, it's kilomoles. We'll convert it to mole. So in the denominator, multiply by 10 to the power 3. That becomes 10 to the power minus 3 in the numerator. Fine. The unit is kilogram per mole. Then we'll come to the denominator. That's going to be the gas constant. The universal gas constant is 8.314. The unit is Newton meter upon mole Kelvin. Fine. And then we have the temperature. The temperature here is the first one is 45 degree. If we are calculating for 45 degree first, then it's going to be 45 degree. So we convert it to Kelvin. Okay. So for converting it to Kelvin, we can use 272.2 plus 45 degree. 43 plus 55. It's going to be okay. So we can use 273.2 plus 45. That's going to be 318.2 Kelvin. And if we use this here, then we'll write 318.2 Kelvin. Okay, so all units are in the same system. So now we can calculate this one, and 10 to the power 5 multiply 28.966 into 10 to the power minus 3, right? Divided by, in the denominator, 8.314 multiply 318.2. Okay, so the value we'll obtain is 1.095. The unit will be kilogram per meter cube because it's a density, right? So first we have obtained the density at dry state. Okay, now we want to obtain the density at some moisture content, that is 50% relative density, right? So relative humidity. So in that case, now we'll use this formula to calculate it for the 50% relative humidity. So rho d moist, if we can write, that's going to be rho d that we have calculated 1.095 in kilogram per meter cube minus 0.611 WA, that's going to be molecular weight of dry air, and it is 28.966. These two are, we can keep in the same units, and WV is going to be 18.016, right? Minus 1, then we have exponential term, and it's going to be 17.27 multiplied by T minus 273.2. That's going to be 45 only, divided by t minus 336. So 318.2 minus 36. Can close this one. Then we again have WV. It's going to be 18.016. Multiply relative humidity is going to be 50%. That's zero point 0.5 divided by the R value, gas constant 8.314. Okay. Okay. So here 18.016 is there, and at the denominator we have, so at the denominator the value of R is, your gas constant have a unit of mole, so we'll convert this kilomole to mole. So we'll multiply it by 10 to the power minus 3. Then we have the gas constant 8.314, multiply with the temperature. Temperature is given here 318.2 for 45 degrees. Okay. So by doing this, now we can just solve it. So it will give you, first let's solve term by term. So 0.611 multiply 28.966 divided by 18.016 minus 1. That will be 1.095 minus 0.371. Multiply this exponential term. So that's going to be e to the power 17.27 multiply by 45 upon 318.2 minus 36. There will be 15.703 multiply the third term 18.016 into 10 to the power minus 3 multiply 0.5. Okay, and then divided by 8.314 multiply 318.2. Okay, so this will give you 3.4 into 10 to the power minus 6, right? So if we'll solve it further, we'll get a value of 0.095 multiply 15.703 multiply 3.4 into 10 to the power minus 3. Okay, and 1.095 minus 0.017. Okay, for the solving, we can get 1.095 minus answer 1.078. The unit will be kilogram per meter cube. So that's the relative density at dry state of the the density of the air, and that's the density of the air at moist state. So that's going to be 1.078. So as we move from dry to moist, the density decreased. Okay. So we have performed this operation for 45 degrees. Now we can perform the similar operation for T is equal to 0 degrees, 0 degrees Celsius. So if I remove this thing, then we'll obtain that for 45 degrees, T is equal for temperatures 45 degrees. We have obtained a moist air density of 1.075, and similar operation if we perform for temperature 0 degrees Celsius, then we'll be using the same formula. We'll be obtaining a relative density of 1.274. Okay, so the question asks that which temperature leads to a higher air density. So the answer to that question will be 0 degrees Celsius. Okay. And it is logical also at 45 degrees higher temperature. And if you go towards lower temperature, then the density will be more. Okay, so that's a little bit lengthy numerical, but I hope you're getting it. And this numerical we also solved in the last class, but I just wanted to revise this one because it was a little lengthy. And with this, we can move on to our next numerical for today. And So the next numerical is that currently the relative humidity in the environment is 80% and the temperature is 22 degrees Celsius. And we need to define the dew point temperature for the given condition. Okay. So currently we have a relative humidity of 80% and the temperature is 22 degrees Celsius. So first we need to determine that what is the UV saturated. Okay. And then we need to determine that how we can reach to the same UV saturated corresponding to 80% RH at what by lowering what to what temperature, right? We need to determine the dew point. Okay, when the dew will be formed, right? So we need to approach which line? We need to approach the saturated vapor pressure line. Okay, so for now we are somewhere here. Okay, and by decreasing the temperature, we need to approach this line of saturated vapor pressure. At this point, we will form the dew, right? So we need to approach from A to B. So first we will determine what is the UV saturated value. Okay, so to determine the UV saturated value, we will use the Tetten's formula, which is given that UV saturated in kPa is equal to 0.611 and exponential this term, which includes the temperature value. Okay, so now the temperature here is 22 degrees Celsius. So we will convert it to Kelvin by 22 plus 273.2. That's going to be 19. Okay, 99 minus 273.2 plus 22. That's going to be 295.2 Kelvin. Okay, so we can calculate UV saturated in kPa will be equal to how much? 0.611 times exponential, and the term inside is 17.27 multiply T minus 273.2. That will basically give you a temperature in degrees Celsius. So we can write 22, and in the denominator we can write T capital T minus 36. So 295.2 minus 36. Let's solve this one. That will be 0.611 multiply. The exponential term will be 17.27 multiply. We have in the numerator 22, denominator 295.2 minus 36. That's going to be 4.33, and it will give you multiply 0.611, 2.64 kPa, kilometer per meter cube. Okay, so we have determined the vapor pressure at saturation. Okay, but the relative humidity here is 80%, right? So we are not yet at saturation, so we need to determine that 80% relative humidity. Okay, what will be the pressure? So what will be the vapor pressure? So to determine for the 80%, we will just multiply this value at point A. If we are saying, then we'll multiply it by zero point 0.8. Okay, that's going to give you 2.117 kPa, like here. So now we know what is the value of this vapor pressure as 80% relative humidity. Okay, but now we do not need to change the vapor pressure value, but we need to determine that how much the temperature should be changed or what should be the end temperature so that we reach the saturated vapor pressure line, the saturated vapor pressure curve. Okay, so for that we'll use the same expression, but this time we will keep the temperature as unknown. Okay, so let's see. So this time what we're doing, we are keeping the temperature as the same and temperature as unknown. So we'll use this expression again, this one, and we can write the UV saturated at 80% humidity is 2.117. That will be equal to 0.611 and exponential 17.27 and this one can be written in degrees Celsius upon T, that's T minus that's T temperature which we need to determine, and to convert it to Kelvin we can write 273 plus 2 minus 36, which is already there. Okay, now if we can solve it, then it will be 2.117 divided by 0.611, 3.465 is equal to exponential, and it will be 17.27 T upon T plus 237.2. Okay, so either we can taking solve by taking ln both sides. So ln 3.465 is equal to 17.27 multiplied T upon T plus 237.2. So ln 3.465 is going to be 1.24 is equal to 17.27 and T upon T plus 237.2. So if you'll solve T from here, then you'll obtain T will turn out to be 18.39 degrees. Okay. So for the same vapor pressure, we were initially at a temperature of 22 degrees. Okay. Now the temperature is dropped such that the end temperature is going to be 18.39 degrees. At that point, you will have the dew formation. So you'll reach the dew point temperature. So the dew point temperature is nothing but 18.39 degrees Celsius. Fine. So the dew temperature which is there, that's going to be 18.39 degrees Celsius. So by lowering the temperature from 22 degrees Celsius to 18.39 degrees Celsius, you can easily obtain the dew, or you can reach to the saturated vapor pressure line, and you can reach the dew formation state. Okay, that's a simpler numerical, I think, in relatively. Let's see if anyone else is joining. I don't think so. So that's the third numerical which we have solved, and now we'll move on to the Henry's law. Okay, so till now we have seen that how much water can be vaporized in air. So we were dealing about the vapor pressure and these terms. Okay, so now the Henry's laws, in the Henry's law we'll be dealing with the second question, that how much air can be dissolved in the water. Okay, so to determine this we usually use the Henry's law. Okay, so the Henry's laws we usually express it with this formulation that describes that mi upon wi upon the volume of the liquid, the molar fraction which is dissolved in the particular volume of liquid will be equal to Kh into Ui. Kh is nothing but the Henry's law constant. Okay, and the Ui that is there, it is nothing but the partial pressure of the gas I. Okay, in so we'll be using we'll be using this expression to determine that how much air is dissolved in water. So with this, we'll be solving, and this Henry loss constant, which is there, that is KHI. It depends on the temperature. Okay, it depends on the temperature that the constant tend to decrease with increase in temperature. So indicating that lesser amount of particular gas may be dissolved as the temperature increases. Okay. So as the temperature will increase, you will be able to dissolve less amount of gas in the water. Okay. And so we'll solve a very simple example to determine that how much nitrogen can be dissolved in a liquid water. Okay, or we'll determine the solubility of the atmospheric nitrogen gas in liquid water at 25 degrees centigrade Celsius. So the solubility is nothing but the molecular value, the mass of the gas which is dissolved in kilograms divided by the volume of the liquid. Okay, so here you'll solve this numerical. And so what's given here, we can make use of table 3.1 to determine Henry's law constant. Okay, and the partial pressure UI of that particular gas. Okay, so we need to determine the solubility. So we'll determine the value of Mn2 upon Vl. Okay, here from this formula, if you will see, we can write Mi upon Vl is equal to Wi, Khi, and Ui. Okay, so the multiplication of three terms. The Wi is the molecular mass of gas I, Khi is the Henry's constant, and Ui is the partial pressure of that gas. So we'll use this formulation and determine the solubility. Okay, so therefore, to determine the solubility of that particular gas, that is nitrogen here, and first we need to determine the molecular mass. Okay, Wi is a molecular mass, kilograms per mole. Okay, to for the nitrogen, we have two molecules of nitrogen, so we can write two, and the molecular weight of particular 14.01. So it will be 28.02, we can say. So here we will write omega n2 as 28.02. The unit will be gram per mole. Gram per mole. Okay. And then we'll move on to the Henry's constant. So for nitrogen, if you will see in table 3.1, the Henry's law constant for different gases that are in air are provided here. So for oxygen, it's 1.26 into 10 to the power minus 3. And for nitrogen, it's 6.4 into 10 to the power minus 4. So the higher is the Henry's law constant, the more is the solubility. Okay, so nitrogen. So here, this CO2 is more soluble than nitrogen. Okay, and the oxygen is also more soluble than nitrogen. Fine. So if we'll multiply the Henry's constant for nitrogen, that's going to be 6.40 into 10 to the power minus 4. The unit is mole per bar. Okay. And then we'll multiply the value of this partial pressure in bar only. Okay, so the partial pressure for nitrogen is given as 0.7808 bar. Okay, so mole per liter. So here it should be mole per liter. Okay, fine. So if now we multiply is 28.02 multiplied by 6.40 into 10 to the power minus 4 multiplied by 0.7808, it will be coming 0.014. The unit will be in grams per liter. Okay, if we convert it to milligram per liter, multiplied by 10 to the power 3, 14 milligram per liter. Fine, 14 milligram per liter. So the solubility of this particular gas, that is nitrogen, in the water is 14 milligram per liter. Fine. In the similar way, we can determine the solubility of oxygen as well as carbon dioxide if we need to determine the question. So till now we have solved the numericals on first the direct shear test. Then we moved on to solve a numerical to determine the moisture unit. Here we are dealing with that uh, how much uh, how much water can be vaporized in the air. Okay. Then we deal with the determination of dew point temperature. Okay. And then we are here discussing the Henry's law constant. So in the Henry's law, we discussed that how much air is dissolved in water. Okay. And now we move on to the concept of surface tension. Okay. So as you all have studied in the theory class that to determine the surface tension, basically when we deal with the surface tension, we deal with the capillarity in soil matrix. Okay. Or in the capillary tube. So when we determine the matrix suction, we use the concept of surface tension. So the matrix suction can be defined as 2 times the surface tension into cos alpha. Alpha is the contact angle upon the R. R is the radius of that capillary tube. Okay. So the surface tension UA minus UW can, for most of the soil, the alpha is nearly zero. Okay, and it's an intrinsic property of any two contacting phases. Okay, that is mostly solid, liquid, or gas system. Hmm. So if we write alpha as zero, then this cos alpha becomes one. So we can simplify this expression for soils mainly. UA minus UW is equal to twice ds upon r. Okay, or maybe the capital R. The capital R is basically smaller upon cos alpha. So we can also write as the alpha is zero, we can write this expression as UA minus UW is equal to twice ts upon small r. That is the radius of the capillary. Okay, so let me erase this one, and then we discuss a problem on the determination of the symmetric suction, or we can say the determination of the pore water pressure or the pore air pressure. Okay, so in this example, first let's discuss about these two figures which are indicated here. So the first system, that is the figure A. Get the pen. So first figure, which is the figure A, what it denotes? It denotes that there is a beaker where the water is there and some air bubbles are there. Okay. So if you'll see here, shape of the air bubble is concave this side and convex this side. So the air pressure will be more inside, right? So if we see the bubble here, the air is inside, so on inside it will be UA and outside it will be UW. Okay, and the pressure will be more on concave side. So here we can say that UA is greater than UW, or the pore air pressure is greater than the air pressure is greater than the pore water pressure. Okay, but when we see the concept in the opposite term, like the water droplets are there in air. Okay, in that case, the inside pressure is UW and the outside pressure is UA. Let's see if we are still connected. Okay, so we were discussing about the pressure inside sorry, pressure inside air bubble as well as the water droplets. So in this way, you can say that UA is less than UW. Fine. So we'll use a similar concept here while solving this numerical. So it says the typical water drop from a sprinkler nozzle are spherical, like in this case, okay, and it has the size is in the order of 0.2 to 0.02 mm in radius. Okay, so if the surface tension of water is given as 72 millimeter per meter at 25 degrees Celsius. Then, and the ambient air pressure is 100 kPa, that is UA. Okay. Then we need to determine what is the highest pressure inside the water drops. Okay. So before we proceed further, we will see that we need to determine the highest pressure inside the, what is the highest pressure inside the water drop. Okay. So inside pressure is UW. So if we write it here, UA minus UW is equal to twice ds upon r. Okay, so the UW will be equal to UA minus twice ds upon r. Fine. So the UW will be maximum when r will be maximum. So this term will be minimum. Okay, fine. So to determine what is the maximum UW in that case, because in the question it says what is the highest pressure inside. So the maximum pressure inside will be when the R will be maximum. So the maximum R is 0.2. Okay, so here to solve this, we'll use the same expression which I wrote here. So UW will be equal to UA minus twice TS upon R, right? But the thing to note here is that okay. Oh, okay. So the thing to note here is that we need to determine the sign of R. Okay, that is relative. So the highest pressure occurs when the in the smallest water drops. Okay, so assigning phase X as air or and phase Y as water. So we'll see that R value is negative because or less than zero because the curvature of the water drops indicate that water pressure will be higher than the air pressure. Okay, so here the water pressure will be higher than the air pressure. Okay, so the R we can take as negative. Okay, and uh, also we can understand this concept in another manner that here we have said that UA is more and UW is less, right? So in that case, we will to determine the UW, okay, what we need to do that because UA is more and the UV is less. So in that case, what we'll do, we'll take the value of the UA and then sum it up the value which we are determining here. Okay, so to solve this, let me first erase this one. Okay, so to determine the value of UW, we'll write UA minus twice TS upon R, and that's going to be 100 minus 2 times 72 into 10 to the power minus 3 to convert it to Newton per meter. Okay, and divided by the radius is going to be minus 2 into 10 to the power minus 5. Okay, so 0.02 mm, if you convert into meter, that's going to be 0.02 into 10 to the power minus 5. Okay, and after that, we'll need to convert this. We'll need to convert it into kPa. Okay, so for that we need to multiply by 10 to the power minus 3 or 1 by 1000 pascals, 1 by 1000. So if we'll solve it here, so we'll obtain 2 into 72 10 to the power 6 in the numerator, 10 to the power minus 5 in the denominator. So it's going to be 10 to the power minus 1 above or zero point 0.1 divided by 2. So 7.2 kPa. 7.2 kPa. So the UW will be 7.2 kPa. So the UW will be 100 minus minus plus 7.2. So it will be 172.2 kPa. Okay. So the other way which we are trying to understand is that the UW is more. Okay. So we will need to add something in UA, right? The something which we'll add is twice TS upon R because that is a pressure difference. Okay. So to get UW, we'll need to add UA plus twice TS upon R. In that case, we'll not need to worry about the sign of capital R. Okay. And also we need to determine if you use this concept UW is equal to U naught plus twice TS upon R, then we'll see that UW maximum will be obtained when R will be minimum. Okay, so here not the 0.2 but the 0.02 will be the value which we'll be using to obtain the highest pressure. If we move on to the surface tension part and pressure drops uh, pressure drop across our air water interface. So here also we'll solve a problem which will be using the same concept to determine the metric suction. Okay, so the example says that assume that air water interface for a certain degree of saturation among particles in fine sand is spherical. Okay, and zero point 0.1 to 0.01 mm in diameter. Right? So the range of the diameter is from zero point 0.1 to 0.01 mm. Okay. If the surface tension of the water is 72, as in the last question at 25 degrees centigrade for Celsius, and the pore water pressure is UA is pore air pressure is 100 kPa. So what is the range of pore pressure in the unsaturated sands? Okay. So to determine the pore water pressure basically depends on the value of the diameter of the spheres, okay, the particle size, okay, the R value, okay. So to solve this, we will use the same formulation. So UW max, if we'll obtain, that will be given by UA minus, here we are considering that R is positive as we are in the air, the air particles, the air bubbles are there in the water. Okay, so we are considering the curvature as positive from this side. Then we'll see that we can obtain the maximum value of pore water pressure when we have the maximum radius. So twice Ts upon R max. So that will be the UA. UA value is 100 kPa minus twice Ts. That's going to be 2 into 72 into 10 to the power minus 3 divided by R max, the maximum R which is there. This is the diameter. So the maximum R which will be there will be for zero point 0.1. Okay, zero point 0.1 mm. So divided zero point 0.1 divided by 2, that's going to be mm. We'll convert into minus 10 to the power minus 3. Okay, in meter. So now we have, if we solve this, we can convert it to multiply 10 to the power minus 3 to convert it to kPa. So that's going to be give us 2 into 72 into 10 to the power minus 6, and that's going to be divided by 0.05 multiply 10 to the power minus 3. Okay, 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 that's going to be give you 2.882. So 100 minus 2.88 kPa. It will give you a value of 97.12 kPa. Fine. So here we have a value of 97.12 kPa for UW max. Okay. Similarly, we'll solve it for minimum pore water pressure. Okay. In that case, UW min will be equal to UA. So UW min will be equal to UA minus twice Ts upon R minimum. So if we solve this again, 100 minus 2 into 72 into 10 to the power minus 3, and to convert it into kPa, 10 to the power minus 3 divided by the minimum value of the R. So the minimum value of R diameter is 0.01 divided by 2 into 10 to the power minus 3 to convert it into meter. So here if we solve it using a calculator, then we'll find 100 minus 2 into 72, 10 to the power minus 3, and 10 to the power minus 3 will get cancelled and divided by 0.005. And if we multiply 10 to the minus 2, then it's going to be 28.8 kPa. So this value will come out to be 71.2 kPa. Fine. So the range of the UW is from 71.2 kPa to 97.12 kPa. Okay, so we needed to determine the range of UW. Right. Okay, so we were discussing about this problem about the pressure drop across in a water interface. So here, if you'll note here that we first determine the UW max, then we determine the UW min, and based on that, we can determine what is the range in which the pore water pressure will vary. And uh, so now we move on to the concept of cavitation and boiling in water. So the cavitation and boiling are identical phenomena, and they describe the same physical results. The physical result is to change from the liquid phase to the vapor phase. But they both differ in the path by which they follow from changing from one phase to another. Cavitation is the process of vapor nucleation in liquid when the absolute pressure falls below the vapor pressure. Boiling, on the other hand, may be defined as the process of vapor nucleation in a liquid when the temperature is raised above the saturation vapor pressure or liquid temperature. So it basically, if we see in the thermodynamic phase diagram of pure water, so this curve which you see here is the vaporization curve. So above which, if you'll see the pressure and temperature condition, the combination of pressure and temperature condition in this region, which is shown between A, B, and C. So in that region, if the water lie, if the pressure and temperature condition lie in this region, then the water will be in liquid state. And if the pressure condition lie below the vaporization curve, then the water will be in vapor phase. And this curve at the this portion at the left side, that is ADC portion, that lies in in this condition, the water lies in the solid phase. So the line between the line which defines the liquid, which divides the liquid and vapor phase, is the vaporization curve, and the line which defines the liquid and solid phase is the fusion curve, and the line which discriminate the solid and vapor phase is the sublimation curve. So if you'll see here, if this is point A and this pressure and temperature condition lie at point A, so we can reach to vapor from liquid phase to vapor phase by two processes. The first one is the ideal boiling path. So by following this, we can reach here by increasing temperature from point A to point B, let's say. And then the second ideal path will be the ideal cavitation path. So from A to C, if we drop the pressure, then we can directly reach to the vapor phase. So the final state is the same. Final state is the vapor state, and the initial stage is the same. That is the liquid state, right? But the process are different. So there are other path also to reach at the vapor stage, right? So there are multiple paths to reach, but the ideal path are the boiling path and the cavitation path. So and the point which is the like this point A, which you see, is the triple point. Okay, the temperature and the pressure as these points are defined at 273.15, and that's going to be 0 degrees Celsius and 0.61 kilopascal. Okay, so we are going to study the next concept which have started related to surface tension. That's going to be the capillary rise. So the formula, as we remember, for UA minus UW is 2T cos alpha upon R. Okay. And if we see here, the formula of the capillary rise in terms of the height of the water in the capillary tube is going to be Hc is equal to 4T cos alpha upon small d gamma W. Okay. The small d is the diameter of the capillary tube, right? Diameter of the capillary tube. And the Kelvin's equation dictates that the suction value, that is UM minus UW, will be equal to 2T cos alpha upon small r. Okay. So if we put D is equal to 2R, then we can reach here. And by bringing gamma W this side, we'll be reaching the pore water pressure value, not only the height. So this can be equated to minus RT upon nu W. Nu W is the dynamic viscosity, ln UV1 upon UV naught. Okay, and if by the diagram, if you'll understand the pore water pressure in the capillary tube, then we can see that at the point of the free surface, the pore water pressure is zero. Okay, and if we go below, then we'll see the pore water pressure increases as the depth or the height increases. So that's going to be H into gamma W. Okay, and this side we are assuming that the pressure below the free surface is positive, pressure above the free surface is negative. So if we move above, that's also going to be H into gamma W. Right, so both are same. Again, if you see from this diagram, then at this point, the pressure is going to be P is equal to P atmospheric. Okay, and all the points are at P atmospheric, and the top also, the pressure is going to be P atmospheric. Okay, but if we'll just go below this top surface, then the pressure going to be P is less than P atmospheric, right? And this is the contact angle theta. Okay, and if we go in between the point, or we can say the medial height, then P will be less than P atmospheric. So the capillary rise we studied from the Kelvin equation can be written, the matrix section can be written like this, and based on this we can determine the capillary height. So the thing here, thing to note here is that the matrix section in a capillary tube, or the capillary height in the capillary tube, depends on the diameter of the capillary tube, as well as the surface tension between the of the surface tension of the liquid, as well as the contact angle. Okay, so if we see here in this illustrative diagram, when the diameter or the radius of the tube is bigger, okay, than this one, so R1 is greater than R2, in that case the height of rise is lesser, right? So as the diameter of the tube gets on decreases, as the diameter of the or the size of the capillary tube decreases, the height of rise increases. Okay, so with this concept we will solve a numerical. The numerical is the pore water meniscus between two sand grains, which are shown here, at a certain degree of saturation can be characterized by two spherical radii. Okay, so the two spherical radii can be R1 and the second one is R2. Okay, and the R1 is given 10 to the power minus 6, R2 is given 10 to the power minus 3 meter. Okay, so R1 and R2 are given. We are assuming that contact angle is 0. So the temperature contact angle alpha is 0 degree, and the temperature is 25 degrees Celsius, and the pore air pressure in reference value is 0. So UA is equal to 0. So let's see how we can solve it. So here we'll use the another form of this equation, that is for the pore water pressure, that is for the matrix suction. So let me write here, UA minus UW is going to be surface tension 1 upon the radius or the first radii upon 1 upon R2. So the TS value of the TS is approximately 72, okay, 72 millinewton. So we'll convert it to Newton by multiplying 10 to the power minus 3, and we'll take the radii as 1 upon 10 to the power minus 6 minus 1 upon 10 to the power minus 3. So that we can write 10 to the power 6 minus 10 to the power 3. And if we'll solve it, then we'll obtain that's going to be 72 into 10 to the power 3 minus 1. 71928 Newton per meter square. So if we convert it to K2A, that's going to be 71.928 kilonewton per meter square or 71.928 kPa. Fine. So, we have determined it as 71.928 kPa. Okay, let me just erase it real fast. Okay. So, if we see these values in our already solved example, okay, so we determine the UA minus UA minus UW value as 71.72 or 72. Okay, so now the question is saying what is the corresponding pore water pressure? And this one we have solved. The repeat the analysis for the system at a lower degree of saturation, where R1 decreases to 10 to the power minus 8, this one, and the R2 decreases 10 to the power minus 4. So this one. Okay, so R1, R2 values have decreased. So now we'll do the same analysis for different R1 and R2 value. So UA minus UW is equal to the value of the surface tension. That's going to again 72 into 10 to the power minus 3, and it's going to be 10 to the power minus 8. R1 is 10 to the power minus 8, and R2 is 10 to the power minus 4. So if we solve it again in the kPa, then it's going to be 10 to the power 8 minus 10 to the power 4. Okay, so it's going to be 7178 kPa approximately. Okay, so the corresponding pore water pressure if we'll determine, that will be equal to, here also UA is equal to 0, so pore water pressure is negative of, and here also, so pore water pressure will be negative of 7178 kPa, as pore pressure is 0. Okay. So in this question we have seen that if we know the two radii, okay, R1 and R2, two is the radii, then we can determine that what is the value of metric suction. In turn, the value of pore water pressure. Okay, so now we move on to the another numerical that will be based on the Kelvin's equation and the other expressions regarding the values of these relative humidity. Okay, and that is the UV upon UV naught. So that is the pore pressure at saturation and pore pressure UV. So now we'll see how we can solve this. So the problem says that as shown in figure 3.13, water droplets with initially different sizes ranging from R 10 to the power minus 5 to 10 to the power minus 8. Water droplets are of different sizes are in a container. That activity sustains an ambient relative humidity of RH is equal to 101%. What will be the final size of droplets at equilibrium? Okay. So we need to determine that at equilibrium, what will be the final size of the droplets. Okay. So for this, if we'll see that we already know the value of relative humidity, Okay, and in this term, if we'll see, we know the value of the gas constant, we know the value range of the radii. In between, we need to find the radius, and we also know the temperature. Okay, at what we are trying to, let's see if we know the temperature. Okay, so it says droplet initially different sizes. A container actually sustain ambient temperature, ambient humidity. What will be the final size of droplets at equilibrium? Okay. So what we can do here is that we already know that the value of alpha is 0. So this term will be 1. And the other values we already know from knowledge. Then we need to find that we need to find the um, value of this relative humidity uh, at different radius ranging from 10 to the power minus 5 to 10 to the power minus 8. Okay, or we can go a little further also. So okay, so if we'll solve this question, okay, so in this problem, I think the temperature value is the one which is not known. So we'll come back to this problem later, maybe, or in the next class, we'll solve this problem again. I'll have to check the temperature values for this problem. Okay, so before that, let's move on to the capillary condensation, and we'll be making use of these three questions which I shown in the last class, last slide, and then we'll be solving a question on the side that. Okay, so before understanding that, if we'll see that if a capillary tube is there, uh, let's say in a near a water tank, then we'll see because of the low pressure inside the capillary tube, slowly the water particles, the water vapors, they will start coming inside the capillary tube, and the water will be condensation. Water will start the condensating inside the capillary tube. So slowly the capillary tube will start filling up. Okay, so it basically happens because of the suction inside the or the low pressure inside the capillary tube. So if we would like to solve a question based on this, then the example says that that uh, assume that the capillary tube system introduced above is described by the following state and material variables. So the radius is given at 10 to the minus 9 meter. The temperature is 298.16 Kelvin. The value of alpha is 0. The dynamic viscosity is given here, and the value of gas constant and the value of surface tension is provided here. Now we need to calculate the equilibrium vapor pressure, matrix suction, and relative humidity. So the first formula that we are going to use, let's say we start from calculating the matrix suction. Okay, so let's use this formula that says UA minus UW is equal to twice Ts cos alpha upon small r. So twice the value of surface tension is provided at 72 millionewton per meter. So let's convert it to Newton. Cos 0 degree, that's going to be 1 upon small r, that's going to be 10 to the power minus 9. So if we calculate this value, 2 into 72 and divided by 10 to the power minus 6. Okay. So, if we multiply 10 to the power 3 to convert it to kPa, that will give you the value of 144,000 kPa. Okay. So we have determined the value of matrix suction, that's going to be U minus UW is equal to 144,000 kPa. Moving on to the value of relative humidity, that's going to be obtained from this formula. So let's find some space to write. And so the relative humidity is equal to exponential of minus 2 times the TS value, the surface tension, 72 into 10 to the power minus 3 Newton per meter, multiply the dynamic viscosity 0.018 millimeter cube per kilomole. So that's multiplied 10 to the power minus 3 again. And the cos alpha will anyways be 1 divided by small r, that's going to be 10 to the power minus 9 meter, and capital R, the gas constant 8.31432 joule per mole Kelvin, applied by the temperature, that's going to be 298.16. So we'll need to solve this. That will come exponential of 2 into 72 into 0.018, okay, 10 to the power of minus 6, 10 to the power minus 9 below, and divided by 8.31432, okay, and divided by 298.16, okay, and multiplied by 10 to the power 3. That will be 1.045. So it will result into e to the power 1.045. So it will be around, that's going to be minus. So e to the power minus 1.045. That's going to be around 0.3517. So the relative humidity will be approximately 35%. Okay. So if we know the value of relative humidity, then we already know the value of UV upon UV naught. Okay, so here we were asked to calculate the vapor pressure. So we know the value of vapor pressure, the ratio, relative vapor pressure or the relative humidity. So the UV we do not know, but we know the value of UV naught from this table. So if we see for the temperature 298.16 in this table, so this is approximately 290.16. Corresponding to that, the UV saturation is provided at 3.167 kPa. So from here, we can write UV is equal to 3.167 multiplied by 0.35. That's going to be 3.167 multiplied by 0.35. So that will be 1.08 kPa. So set at 1.11 kPa. So in this question, we have solved three quantities. First one is the matrix suction, which is solved using this formula of Kelvin. And the second one is the relative humidity using this formula. And the third one is the U naught, UV, sorry, the vapor pressure. So if in this question, if anyone is having any doubt, kindly let me know. Or you people can try solving it once by your own. Sorry for that. And with this, we'll be moving on to the concept of matrix section in more detail. So, the matrix section is basically having two parts. The total section is basically having two parts. The first one is the matrix section, and the second one is osmotic section. So, it is basically denoted by psi. Psi is divided into psi n and psi naught. Okay. The matrix section part is because of the soil matrix, and the osmotic suction part is because of the salt present in the matrix. Okay, so uh, we we usually characterize the soil water characteristic using soil water characteristic curve that is called as WCC or water retention curve WCC. Okay, and this basically represents the important constitutive relationship of unsaturated soil. This is between the volumetric water content theta and the psi soil section psi. So this should be theta. Okay, and and what it denotes is that if we start from a little more than the saturated volumetric water content, saturated soil, so we start from water content at saturation, then we'll try the sample and we'll see here it will follow this path. But when we'll again follow the wetting cycle, then the path will be little different from the drying cycle. So the new water content at the end will be lesser than the saturated water content, volumetric water content. And this will have a hysteresis type of nature. So if we'll dry it again, then it will go like that, then it will come back again in the wetting cycle. Okay. So this curve is called the soil water characteristic curve. Okay. And the second concept which we are going to study is the capillary rise in the idealized soil. So we have studied the formulas like here for the capillary rise. Those are UA minus UW is the matrix suction. That's 2 STS cos alpha upon R. So if we calculate from here, that's capillary rise is going to be 2 ST cos alpha upon R gamma W, right? So we can use the same concept of capillary rise for the soil matrix also. Okay, so for soil which is having the same size of grains, if we uh, if we follow the first type of filling pattern, no, that is the simplest filling pattern, is simple cubical form. So in this form, you'll see there are four soil grains, and this is the space which is left. So we are assuming that the pore space is circular. So if by this formulation, if you'll see in this triangle, if we apply cos 45, that's going to be the d by 2. Okay, L, that is going to be d by 2. So the base and the hypotenuse, that's going to be d by 2 plus, if this is dsc, so dsc by 2. So d by 2 plus dsc by 2. Okay, so now, if we'll solve this one, then we'll obtain the radius of the pore space DSC is going to be 0.41 times capital D. The capital is the D is the diameter of the soil grains, and capital is diameter of the soil grains. So we can simply say that the diameter of the pore space DSC, that is equal to 0.41 times or approximately the half of the size of the grains. Okay. So with this, we start with the value of for the simple cubical arrangement. Then the second arrangement, that is the simplest or the densest arrangement, is the tetrahedral arrangement. In that arrangement, you'll see the triangle will remain the same. Okay, but this contact angle, if you'll say it was 45-degree here and 30-degree here, so the contact angle will change. So if you apply the same, if we write the formulation of cos 30-degree here, then we'll find it's going to be d by 2 divided by d by 2 plus again it's small d tetrahedral 1 2, right? So if we'll solve this, then we'll obtain d tetrahedral is going to be 0.15 times of the grain size or the grain diameter. Okay. So what we observed here from here is that the pore size in the simple cubical pattern is 0.41 times the grain diameter, and the pore size in the tetrahedral is the 0.15 of the grain diameter. Okay, so it's significantly less. So this one is the loosest packing, we can say, and this one is the densest packing. So now we'll use this formulation to determine the capillary rise in the soil skeleton, okay, with several approximations. So a more realistic system of a spherical particle would likely have a packing geometry that falls somewhere in between these two limiting cases. The first one, that is simple cubical, and the second one, that is tetrahedral. So, sorry, so the most uh, realistic system will have the combination in between these two, right? And a set of combinations also. So if you'll see here, the formula of capillary rise, that's going to be 4Ts cos alpha upon D rho W into G. So in this one, if we let me check the recording, okay, what's going on? So in this one, if you'll see, now if we apply here for the DSC case, then we'll see HC will be equal to, for the simple cubical pattern, 4 Ts cos alpha upon the D value will become 0.41 times diameter into rho W into G. Okay, that's going to be 4 upon 0.41, 9.76 times Ts cos alpha upon capital D rho W into G. Fine. And similarly for tetrahedral, simple cubical, and for tetrahedral, if you will see 4 upon 0.15, and the remaining expression will remain the same, d rho w g. That's going to be 26.67 ts cos alpha upon d rho w into g. So in these two limiting cases, the HC will be varying from this to this. So now if we put some standard values like for the water, rho W is 1 gram per centimeter cube, G value is 980 centimeter per second square, and TS is 72 millinewton per meter. So if we put that in these equations, then we'll obtain that height of the capillary rise is equal to, is will vary from 0.73 upon D uh, and 2 upon D, right? So this one is for simple cubical and this one is for tetrahedral. So what we observed here is that for simple cubical, height of rise is lesser than the tetrahedral. Okay, that's also logical because when we have in the tetrahedral, we have the small diameter of the capillary tube, and here we have larger diameter. So in the smaller diameter, the UA minus UW or the section value is more, and in greater diameter, it's less. Okay, so with this, if we can solve the problem provided in the assignment. So here it is given that a soil is uniform, the grain size is 0.002 mm, the grain size. So it's basically diameter. So if we write DSC and they are arranged in simple cubical pattern. So that's going to be DSC is 0.41 times capital D. So it will be 0.41 into 0.002 in mm. 0.41 into 0.002. So 8.2 into 10 to the power minus 4 mm. Okay. And the capillary rise we need to determine. Everything else is provided like surface tension, standard temperature, etc. So here if we put HCS4 into the temperature, the surface tension that's given 72.75 into 10 to the power minus 3 into alpha is can be assumed as 0, so cos 0 degree divided by the diameter that's going to be 8.2 into 10 to the power minus 4 in mm, so we'll convert into meter and the rho wg can be written as gamma. So gamma is 9.81 kilonewton per meter cube. So we'll convert into meter, Newton per meter cube. So if we solve this, that's going to be 4 into 72.75. So 291 into 10 to the power minus 3 divided by 8.1 into 9.81, 80.442 into 10 to the power minus 4. Okay. So if we further solve this, that's going to be 291 upon 8.044. So the height of capillary rise is going to be 291 divided by 8.044. So that's going to be 36.176 meter. Okay. So here none of the none of the options have this value. But the height is going to be 36.176 meter. Okay. The second question says that there are two uniform soils, A and B, both having similar grain sizes. Okay. So the D value is same and same geometric water content, same gravimetric water content. Okay. So considering soil A is arranged in simple cubical pattern. Okay. This is simple cubical pattern and the soil B is arranged in tetrahedral pattern. Okay. Then we need to take which one is correct. Hmm. So in the simple cubical pattern, as we know that the pore size is more, and in the tetrahedral packing pore size is less. So therefore, the suction value here is less and suction value here is more because the suction value, as we have seen, depends upon R, or we can write 4 times diameter. Okay, so it basically depends on diameter. So diameter here is more than the diameter here. That's why the suction value for the SC or the soil A is lesser than the suction value of soil B. So we can write the suction value of soil A is less than the suction value of soil B. Fine. If you have any doubt in this one or in this one, please let me know. So we move on to the next concept which we are studying, and that is the contacting sphere model. We have already studied And this model, these two models, which are on simple cubical and tetrahedral, packing in 2D was provided by Deleville in 1943. And he have also provided the formulations for metric suction based on the packing here. Okay. And apart from that, he gave two formulations for water content in simple cubical packing, this one, and water content in simple in tetrahedral packing. So if we'll observe these two formulas, then we'll see if we multiply the first formula by 2, we observe the second formula. This indicates that in the simple cubical packing, the water content is half of the tetrahedral packing, right? So water content in simple cubical packing is going to be 50% of the water content in tetrahedral. Okay, or we can say opposite, that the water content in tetrahedral packing is going to be 2 times of water content in simple cubical packing. So these are the two ways to say that. Okay. Now, the third question as says, for a uniform soil mass, the gravimetric water content in simple cubical packing is 50% of the gravimetric water content in tetrahedral packing. So this is correct, as we have seen earlier. So gravimetric water content in simple cubical is 0.5 times gravimetric water content in tetrahedral. Okay, so this assumes that filling angle is same for both soil packing. So that's going to be a true statement, right? I hope you are getting this one. Moving on to the fourth question that says, when filling angle of the soil increases, the suction for a given uniform soil arranged in tetrahedral packing increases. Okay, so again we can take reference from the same figure. Okay, that is UA minus UW for tetrahedral, UA minus UW for simple cubical. So suction is very less in simple cubical than compared to tetrahedral because the size of the capillary is more, size of the capillary is less here. In that case, if we'll see, as we increase the angle from 30 degree to 45 degree, or uh, filling angle of the soil increases. So as we increase the angle, suction decreases. Okay, but here it says the suction increases. So it's not a correct statement. It should be that the when filling angle of the soil increases, the suction of the given uniform soil arranged in tetrahedral packing decreases. Okay, so this is going to be a false statement. The theories which we are studying, these are provided by Delaware in 1943, and you can say simply observe from the figure that these theories are provided for the uniform grain size, or the grain size, not a uniform grain size, but all the grain sizes which are of same sizes. So uh, yeah, a uniform grain size distribution is when they all sizes of particles are present. Okay, so that's well graded soil. Okay, so this is uniformly graded soil. So the particle size of only one type of particle size are present in the matrix. Okay, so we can say that Delival theory is used to stabilize soil water characteristics in uniformly graded, not the well graded, uniform graded. Okay, so in that case, this is statement, if you'll see, in both the formulation, we only use particles of one size. Okay, all the particles in one formulation are of capital D. If this one is D1, so all are D1. Fine. So this statement is considered as false for that. Now, there's a sixth question that says the vapor pressure lowering depends on the capillary size or the diameter of the capillary tube. Okay. So, if you observe here, this illustration which we have seen, the uh, lowering of the vapor pressure, the rise in the capillary tube. Uh, when the vapor pressure is lower, the rise is more. Okay. So the rise in the capillary tube it depends on the diameter or the radius of the capillary tube, right? Which we can also see from the formulation provided by Tatens. That U minus UW basically depends on the radius or the diameter of the capillary tube, right? So this statement is considered to be correct. Okay, this formulation is of my use here. This is not the Tatens formula. This is Kelvin's equations. Okay, so we can also see this from this illustration as the size of the capillary tube decreases, the height increases, the height rise increases. Okay, so for the sand particles, the suction is less. For the clay particles, the suction is very high. So the rise of height rise will be very high here and very less here. And this is in between. Second question says the consolidation test was conducted on two duplicate bentonite samples using distilled water and NaCl solutions as inundating fluid. Okay, and on the same loading condition. So under such condition, the equilibrium void ratio in the case of water is less compared to the that in case of NaCl solution. So we'll understand it by just revising one concept that the let's leave this part. And if you see the consolidation test, then we'll see we have the soil sample here. Let me change the color. So we have a soil sample here.